If my screen sharing drops, just say something, because when I did it for the earlier class, it dropped a couple of times. So just let me know. Where are we? Okay. All right. So go ahead. All right. So yeah, so we left off and we've talked about calculating specific heat. We've calculated specific heat capacity. We've also talked about calculating delta H and writing a balanced thermochemical equation, which we did. We're going to talk more about that today. And so I want to start out talking about calorimetry and enthalpy. So calorimetry is the way we study enthalpy. It's a process that we use to determine the heat either given off by a reaction or absorbed, and we measure those temperature changes. And in doing that, we're able to determine Q, which we can also relate to delta H, which we've done already in a previous lecture. So the way we study heat and delta H and Q is inside of what we call a calorimeter. And that's a vessel, normally it's a sealed vessel. We used to do this calorimetry lab years back when I first started here. And really all you need is a styrofoam cup and a lid to keep the heat from escaping, and a temperature probe, a thermometer. So what a calorimeter is basically a sealed up vessel. It's got a probe or a thermometer, and then you either add a warm body to it and measure the heat exchange between the warm body and the water that's in the calorimeter. And what you typically will do is determine the specific heat capacity of that warm body by adding it to the calorimeter, which contains water and a certain amount of water. That way you can know the mass of the water as well as the specific heat capacity, because that's a known value. We may start back doing that experiment. I'm not sure. But anyway, the calorimeter is how you measure heat given off or whatever, and you measure the temperature change, you know the mass, you know the specific heat of whatever you're using. You can either look for it or solve for it. I'm gonna show you that too. So yeah, so normally we've already talked about some of these terms too. Heat capacity, which is C, which we defined as the heat divided by the change in temperature with no mass component. And then we talked about specific heat capacity, which is the heat or the energy divided by the mass times the change in temperature. And we talked about that being 1 gram of a substance, the amount of energy to raise the temperature of 1 gram of a substance by 1 degree Celsius. So we talked about that. And then we also talked about molar heat capacity. Well, we haven't talked about that, but that's another derivation of specific heat capacity. The only thing is you swap out, you can see right here, instead of mass, wrong pen, sorry. Instead of mass, you have moles, right? So all of these calculations are easily manipulated. You can see right here, you have specific heat, which is Q divided by the mass times the change in temperature. And you can take that, and if you have any 3 of those 4 things, you can solve for the 4th one, right? And that's what all these little derivations are here. Like, these are just ways to manipulate that specific heat equation, right? So let's look at a calorimetry problem here. And there's some things that we're going to talk about as far as the specific heat capacity and what some things that we can assume based on the information that's given. right? So for when you want to measure specific heat capacity, again, in a calorimeter, if you know the heat capacity of the water and the mass of the water and the change in temperature of the water that you can measure with the thermometer and the change in temperature of the warm body that you're adding, then you can solve for the specific heat capacity of that thing. So that's what this problem is illustrating. So it says a piece of copper has a mass of 19 grams and you heat it to 87.4 degrees Celsius. Then you place it in a calorimeter that consisted of 55.5 grams of water. So you need that mass at 18.3 degrees Celsius. And it says the temperature of the water rose to 20.4 degrees Celsius. So what is the specific heat capacity of copper? So here's the thing, right? When you add in the copper that you've heated, right, and it's 87.4 degrees, when it hits that water, it's going to equilibrate to the temperature of the water, which is 18.3. And then the water is going to also cause the temperature of the water to go up, and that's where the 20.4 comes in. But if you, as you leave it, it really is going to equilibrate back down to 18.3. So everything is at the same temperature. And so this is and based on that assumption and based on what we know about that, that's how we can set this equation up. Because if the heat lost by copper is the same as the heat gained by water, then the two Q's are equal, right? So Q water is equal to Q copper. And because of that, we can set the equation up like this and solve for this, right? Because that's what the question asked us. It says, what is the specific heat capacity of copper? So since copper, you add it to the water, and eventually they're both going to have the same temperature, the heat that's given off by copper is going to be the same as the heat that's gained by water. So you set the Q's equal, and then you can solve for the specific heat of copper, right? Just by manipulating it. So basically, if you recall the equation from up here, this is the equation for specific heat, Q divided by mass times change in temperature. So if you're looking for Q, then you use this equation here, right? Q is the specific heat times the mass times the change in temperature. If you know that, then you set this up that way. And then you just solve for the specific heat of copper. So it's this equation divided by the mass of copper and the change in temperature in copper. So that's what the bottom term, the denominator is here. All right. So then it's just a matter of plugging in numbers. The 4.18 joules per degree Celsius times grams, that is the specific heat of water. And then the temperature of water went from 18.3 to 20.4. So that means that you increase the temperature of the water by 2.1 degrees. And then the mass of water is here 55.5 degrees, right? And then we have the mass of the copper, which was given at the very beginning, 19 grams of copper was heated. And then we have here the temperature change in copper, because copper is going to match, the temperature is going to drop to whatever the initial temperature of water is. So T final is going to be 18.3 and T initial is going to be 87.4, right? So that way you get the temperature change here, and it's just 69.1 degrees. When you calculate that, you find out that the specific heat of copper is 0.38 joules per degree Celsius times grams, right? And all of that is based on, again, the fact that when I add something to a calorimeter, the heat lost by whatever that hot body is the heat gained by the cooler body. Because when we talked about heat, we said that heat is the transfer of thermal energy. So anytime a warm body transfers thermal energy to a cooler body, that's what heat is, that transfer of energy. All right, so we know how to calculate the specific heat of a substance if we know the mass of that substance and we know how much the temperature change of that substance is. We don't have to know Q if we're doing this in the calorimeter, because the calorimeter, again, that's where the heat exchange is taking place. And because of that, the Q for the warm body and the Q for the cold body are going to be the same, right? Any questions about that? All right, let's do another example. And this is just a specific heat example with a different substance. So here we have potassium perchlorate, and it says it's used as an oxidizer in fireworks. How much energy in joules, so that's the question, is required to raise the temperature of 10 grams from 20 degrees Celsius to 900 degrees Celsius, and it's giving us the specific heat capacity, 8.811 joules per degree Celsius grams, right? Anytime you have a substance that specific heat capacity C sub S, you can find that. That's a known value. It's actually specific heats have been calculated for many compounds or many substances. So you can find that on a table, or you can Google it, but the information is there. All right, so here's our equation right here. Here's the manipulation to find Q. And so this is just a matter of understanding what delta T is, which is the change in temperature from 20 to 900. And then what is Q, which is given, CS, which is given, and then the mass, right? So it's 7,096 joules or 7.1 kilojoules. Now let me explain this. We've talked about this already. So if I have 7,096 joules, that's the same as 7.1 times 10 to the third joules. And then we know that the 10 to the third, the prefix for that is K or kilo. So that's why I can write that number in kilojoules, right? So 7,096 is the same as 7.096 times 10 to the third. And again, 10 to the third or 1,000 is the prefix for that is kilo. So we can just put a K in front of that and convert it, and it's 7.1 kilojoules. And you'll see some of these examples are gonna kind of oscillate between joules and kilojoules, but don't get freaked out by that, because the standard measurement for energy is in joules, but rather than report these big giant numbers, a lot of times they're reported in kilojoules. All right, so let's go to here. And this is another piece of information that we need to talk about with calorimetry, and that is when you calibrate your calorimeter, the heat capacity for the reaction and the heat capacity for the calorimeter are the same as long as the volumes are equal. So if you're adding in something to a calorimeter that has a volume of 50 milliliters, as long as that's the same and it doesn't change, whatever heat you calculate for the reaction is the same for the calorimeter. All right, that's not a groundbreaking. It's just a piece of information that we need. All right, so now let's think about how we tie all this into enthalpy and how we tie it into calculating enthalpy. So let me change this. This is actually, I think I kind of hipped y'all to this the other day, but wherever you see that D, it should be a Greek delta, so delta H. All right, so any reaction that we do, we've talked about this already, is going to either release heat or absorb heat. If it releases heat, it's exothermic. This means that your final temperature will be less than the initial, right? That's how, when you have something that's exothermic and releases heat, it might start out hot, but then it's going to cool off. That's how you indicate release of heat when the temperature drops. And so this is going to have a delta H that is negative. Right? Same thing for going from, and let me put an arrow here. Hold up 1 second. Right, same thing here. You go from reactants to products, but you absorb energy or you absorb heat. That means the final temperature is going to be higher, right? And so here, this is what we call endothermic. So delta H, because that final temperature is higher, delta H is going to be positive. Right, so anytime we're dealing with delta H, we can know if a reaction is endothermic or exothermic based on whether or not delta H is positive or negative. And we also talked about this the other day when we were writing these thermochemical equations and how to balance it. So this particular equation, you can see that the only thing we do in the case of this, writing this thermochemical equation, is to include enthalpy calculation with the equation to show how much heat was either lost or gained. I don't know why this is not working. There we go. All right, so you see that's methane plus oxygen going to CO2 plus water, right? The delta H for this reaction is negative 890. All right, that means that this is an exothermic reaction. It's going to release energy, and the enthalpy is, or the heat of the system is decreased by 890 kilojoules when that energy is released. Right, so this is the thermochemical equation, is the equation itself plus the delta H, or the amount of heat that was released or gained by the reaction. Now, here's the thing about enthalpy, and here's how we can apply it to a reaction. So we can calculate the enthalpy of a reaction, right? So delta H reaction, which I have here written out, is the heat per mole for that reaction at constant pressure, right? Because at constant pressure, Q and delta H are the same, right? And for any given reaction, the delta H is going to be based on the limiting reactant. Right, so it's going to be based on whatever reactant is the limiting reactant. So that's one part of the idea. So we talked about calculating specific heat. Now we're talking about calculating enthalpy for a given reaction, and how it ties into specific heat. Because if we know specific heat and mass and change in temperature, we can find Q. And if we know Q, then we can use that information to find delta H for any given reaction, right? So at constant pressure, Q and delta H are the same. And so this is our expression, right? Delta H for any given reaction is Q per mole, or the heat per mole, and it's based on the limiting reactant. All right. So look at these two equations right here. This brings up another idea about enthalpy, and that is that it's a state function, right? What that means is that it depends on the state of the matter that you're studying, whether it's at a certain pressure, a certain temperature. It's condition dependent. How much of it, All of these are what we call, remember the other day we talked about this, extensive properties, right? They're based on some amount or some condition, right? So enthalpy itself is a state function. And the way you see that is here, right? You can see in this reaction here, all the coefficients are different. This is the coefficient for methane is 1, 2 for oxygen, and 1 for CO2 and 2 for water. And the delta H is negative 890. If I double the coefficients, notice what happens. The delta H here is 890. Delta H here for the same reaction, but with double the amounts, is negative 1780. So doubling the coefficient also doubles the delta H, and that's a consequence of it being a state function. In other words, the more starting materials I have, the more heat is going to be given off. If I lower the amount of starting materials, then it's going to lessen the amount of heat that's given off because it's a state function. All right. And the reason I'm bringing that up is because the next set of problems that we work, if those problems are going to have in them where we have to increase the enthalpy or decrease the enthalpy, especially when we do the Hess's law problem. It's going to show whether or not we have, if we have to multiply by 2 or divide by 2, then we have to do it for everything, including the given enthalpy amount. All right, questions up to this point? Anybody about anything? But I think the key here is to understand that the delta H reaction is, you base it on the limiting reactant. Right, that's going to help us with when we apply this to a problem, which we're going to do in a second. All right. All right, let's go to here. I should, right, so here, this is a enthalpy problem, and this is the balanced equation. And it's telling us that in the problem, it says that when 2.31 grams of phosphorus with a molecular weight of 30.97, it says a molecular weight of 30.97 reacts with excess Cl2. So that's a clue right there. That's telling you that phosphorus is the limiting reactant. And so we're going to base our heat of reaction, or the delta H for the reaction, on phosphorus. All right, it says it reacts with excess Cl2. If you think about it, with the delta H being a state function, if we based it on chlorine and not phosphorus, we're going to get a different number, a higher number, because it's based on the amount. And but that's not going to give us an accurate delta H for that reaction, because it's based on the excess reagent and not the limiting reagent. Because think about it this way: when the reaction is going, even when the limiting reagent is used up, the excess is still going to be able to give off some heat, right? And so you don't want that. So the number is going to be inaccurate. So it says it reacts with excess chlorine gas to form PCl3 in a calorimeter. So it's a calorimetry problem with a heat capacity of 2.16 kilojoules per degree Celsius. So notice it's giving us heat capacity and not specific heat capacity. So the masses don't really factor in here. All we need is the heat capacity and the change in temperature to find Q. And it says the temperature rises by 11.06 degrees Celsius. Write the thermochemical equation for the reaction. So we're going to come back to that part at the end. But the reaction itself, in order to solve for delta H, we have to find Q first. And it gave us everything we needed for Q, because if we use the specific heat, which is this equation right here, we can just rearrange that to solve for Q. So that's this right here, C times the delta T equals Q. And for, again, constant volume, constant pressure, whatever the calorimeter heat capacity is, that's the capacity for the reaction. So it gave us that. It said a calorimeter with a heat capacity of 2.16 kilojoules per degree Celsius. So we're good with that. All we have to do now is calculate Q. So that is, we have C, which is 2,160 joules. And then that's divided by joules per degree Celsius. And then times the delta T, which was given up top as 11.06 degrees Celsius. Right. So we can get that number 23,800 joules or 23.8 kilojoules. That's Q. Once we find that, now we can figure out delta H of the reaction, because based on this, let me go back right here, delta H for any given reaction is based on the limiting reagent and is Q per mole, or the heat per mole, either absorbed or released. So let's go back down to here. We can just stick those numbers in here. Right, we see now it's Q per mole, so 23.8 kilojoules divided by 0.7075 moles. Now, the moles of phosphorus, how do we get that? How do you get moles of phosphorus if you're only given grams of phosphorus and the molar mass? How can we calculate that? It gave us 2.31 grams. Also gave us a molar mass of 30.97. How do we calculate the number of moles from that? All right, and then grams over molar mass. So 2.31 grams divided by 30.97 grams per mole. The grams are going to cancel. We'll be left with moles. So it's 0.075 moles. So that gives us this number, 318.5 kilojoules per mole. Now, because of that, that's fine. But because of, if we look at the reaction itself, there's a 2 in front of phosphorus as a coefficient. So we have to actually multiply that number by 2, because it's a state function and it depends on the amount of phosphorus. So we have to take that coefficient, multiply by the heat that we calculated, and that'll give us an accurate depiction of how much, what the delta H is for that reaction. All right, are y'all following that? Any questions about that? Any questions about enthalpy being a state function? All right. So now when we write that, excuse me, thermochemical equation, we just go back to here and then stick that number in that we calculated. So it's plus 637. And because that is positive, that means that the reaction itself is endothermic. All right. Questions? Any questions about that? So this problem right here just tied in a bunch of different concepts, right? It tied in heat capacity and the calculation of Q, and then also tied in the relationship between enthalpy and Q, or the heat of a reaction, either lost or gained. And it also ties in some of the terminology as well, endothermic versus exothermic. Remember, anytime delta H is positive, the reaction is going to be endothermic. What that means is that you got to add heat. You got to add heat to it. And anytime delta H is negative, that means the reaction is exothermic, right? Which means that you're going to lose heat, right? Or you give off heat. All right. Now let me add a page, because I'm gonna rewrite all this stuff at the end right quick. I'll go back and take it out later, but I don't want to, like, I gotta walk you through this. I don't want to just BS it. So I had to walk you through it. All right, so let's go back to the final concept of that we're going to talk about with respect to thermochemistry, and that is Hess's law. So Hess's law is an idea or concept, basically saying that the overall enthalpy is just a sum of the enthalpies of the steps that it takes for a reactant to go to product. All right, so overall reaction enthalpy is the sum of the reaction enthalpies of all the steps that the reaction can be divided into. I'm gonna talk about that in a minute too, because the example that we're gonna work through, you'll see that what that means. And it's based on the fact that delta H is a state function again, and you can calculate the enthalpy of any reaction that can't readily be carried out in a lab. What that means, all that's saying is you can do certain reactions and look at their delta H values and use those values and the reactions themselves to come up with a delta H for a reaction that you can't carry out in lab, right? Maybe it's too dangerous, maybe it's something, maybe it generates a product that's too explosive, or maybe it generates a product that is hazardous. And so anything like that, you can do other calculations and use those calculations to determine what the delta H is for a given reaction. So that's the example that we're gonna look at. So when we think about Hess's law, this diagram kind of illustrates that, right? So let's say I'm going from A to B, but I can't get directly to B. And so I need to go from A to C, and then C to D, and then D to B, like that. That's what it means by if I can't carry it out in a lab. So all of these different steps have delta H values, right? You got delta H here, you got a delta H here, and a delta H here for each successive reaction. And so with that being said, what all Hess's law says is that the delta H for the reaction from A to B is the sum of the steps, right? And that's it. And so when we think about how to apply this, let me show you how this works, right? So basically, the overall enthalpy is the sum of the enthalpies of all your steps. So if we have a reaction like this, where we take ethanol and we're converting it into formaldehyde and hydrogen gas. All right, those are my two products. Ethanol is my starting material, right? But I can't directly observe this in the lab. And so what I can do, instead of trying to do that reaction, is I can do other experiments that include formaldehyde formation or formaldehyde reactivity, hydrogen gas formation, or methanol reactivity, right? I can do other reactions, and from those reactions, I can derive delta H for that reaction that I have up top. So let me show you what I'm talking about. So you take that reaction, and we'll say that there were 3 experiments conducted to determine the enthalpy. So 3 experiments were conducted, right? So we have one experiment where we took 2 moles of methanol plus oxygen, 3 moles of oxygen, sorry, let me make sure I got the coefficients in. And that's going to 2 moles of CO2 and then 4 waters. And this reaction, when I did it in a lab, had a delta H of negative 1353 kilojoules. All right. Then I did another reaction, and I took formaldehyde, H2CO plus O2, and I got water plus CO2. And the delta H for that reaction is negative 520. All right, and that's in kilojoules. All right, and then I did a third reaction, and I'm showing you this because I want you to pick up on the fact that these are not the reaction that we have shown up here. There are other reactions that involve either reactants or products of the reaction that's shown, and we're going to use those and combine them somehow to get that reaction that's up top. All right, so then we have the third reaction was 2H2 plus O2 going to 2H2O. All right, and the delta H for this was negative 484. All right. So now I have a set of reactions that contain what I need. I have a reaction that contains methanol, right? So I'm going to use that because methanol has to be included. So I need that reaction. I also have a reaction that contains formaldehyde, which is this, right? Let me change the color on that. So I have a reaction that contains formaldehyde, which is here. And notice up here it's a product and not a reactant. So that matters. I'm going to have to do some manipulation in order to get this how I want it, right? And then I also have another reaction, the third reaction that contains H2. Notice here, though, it's also a reactant in the reaction that I studied and not a product, but it doesn't matter. I can rearrange these. I can do anything I need to do to get what I need, basically. Not anything, but anything scientifically possible. So let me show you what I mean by that. So we want the methanol on the left side because up in the given reaction, it's on the left side. We need formaldehyde and the hydrogen on the right side because those are products in the given reaction. So let's take the first reaction and let's manipulate it. We're going to take this because see here, if you look at the given reaction up top, there's only one methanol. The coefficient is 1 in front of everything. So what we're going to do is take this reaction, 2CH3OH plus 3O2, and that's going to give me 2CO2 plus H2O. And delta H is 1353, negative 1353, negative 1353 kilojoules. All right. Now, how do I get that methanol? What can I do to make that 2 into a 1? Anybody? If I want the 2 in front of methanol to become a 1, what can I do to it? I can't just erase it, but I'll have to do something to it. So what I'm going to do is multiply everything by 1/2. So I'm going to stick a 1/2 out here. All right, this is going to ensure that the coefficient is going to be 1 because it's 1 in the given reaction. So it's got to match what's given. It's got to match what's already already given. So I'm going to multiply everything through by 1/2. So I'm take that. So that's going to give me CH3OH plus 3/2 O2. Don't worry about the fractions. We're going to get rid of those later. Plus CO2, goes to CO2 plus 1/2 H2O. Any questions about that? And because this is a state function, I also need to cut that in half. So that's going to be, let's say 677. So now delta H is also going to be divided by 1/2. So not only am I multiplying the whole equation by 1/2, that's also going to cut the delta H value because it's a state function. So if the coefficients change in the reaction, so will delta H. So this is going to be, let's say 676.5 kilojoules. That's the new value after I divide that by 1/2. All right. Now let's manipulate that second equation because we need that one. We need the formaldehyde, which is highlighted in yellow on the other side of the arrow. So we can rearrange that. The stoichiometry is fine, but we need to rearrange it. So what we're going to do is reverse the reaction. We're going to take that and turn it around. So the CO2 is going to come, well, I'm going to write it out. I'll write it out again. So this is H2CO plus O2 going to H2O plus CO2, right? And then it gave us the delta H as negative 484. Is that right? No, negative 520 kilojoules. All right. When I turn that around, everything is going to get turned around, even the delta H. So I'm going to put the H2O over on this side. So H2O plus CO2 goes to H2CO, which is what I want. Now it's in the product side, plus O2. And the delta H is going to go from negative to positive. So now this is going to be positive 520. When I reverse that reaction, I also have to change the sign of delta H. And that's true based on what's called microscopic reversibility. If you go forward and your enthalpy is one thing, when you go in reverse, it's going to be the opposite. Same number, but opposite sign. All right. And now I want to rearrange that last equation right here because I also want to put H2 as a product. So I'm going to rearrange that. And rather than rewriting this one, I'm just going to show it as rearranged. So we're going to rearrange the same way by reversing the reaction. All right, so now I'm going to put 2 H2O plus, not plus, goes to 2H2 plus O2. Now what you'll notice right here is the stoichiometry is off. In the given reaction, there's only one H2. So I'm gonna do the same thing here. I'm gonna take this and I'm gonna divide everything by 1/2, or multiply everything by 1/2. So this is gonna cause the it's gonna make the stoichiometry match. So I'm gonna take that and multiply it through because I only need one H2 in the product. So that's gonna give me H2O goes to H2 plus 1/2 O2. And I'm also gonna cut that enthalpy in half as well, because it gave me a delta H of 484. So delta H was negative 484. When I reversed it, it became positive 484. And then I'm going to multiply by 1/2 because I did that to the whole reaction. So now there's going to be 242 and it's positive. So now I got all my values. I got the enthalpy for this. I got the enthalpy for the second reaction and the first reaction. So I'm set. Now all I need to do is add all this stuff together. So that's that. So 676, positive 676, negative 520, and then positive 242. All right. So now, I multiplied all that by 1/2, cut the enthalpy in half, and now I just need to add these together. And for the sake of time, I'm just going to show it to you because we did it this morning. And this is what it would look like added together. All right, so you had 1 CH3, 3/2 oxygen going to 1 CO2 and 2 waters, and then 1 water going to 1 H2 plus 1/2 O2, and then water plus CO2 going to formaldehyde plus O2. And so now what you see is you can cancel out stuff that's alike, right? So you have the O2s on the right side, 1/2 plus 1 is 3/2. So we're going to cancel out the 3/2 oxygens. Then we got 2 waters on the left side and 2 on the right side, so we can cancel those out. We got 1 CO2 on the left, 1 on the right, so we can cancel those out. And we're left with this equation. And then to calculate the enthalpy, we just add up all the enthalpies from each step, and it's 86 kilojoules plus 86 kilojoules. All right, I know that was a lot, but you can watch it again, go back through it, and if you have questions, you can always just ask. So if you have questions now, you can ask. Even though we're 4 minutes over time, I don't have another class, so we're good. We'll have a lab, but you can still ask. Any questions? So everybody's
I got a question.
Go ahead.
But it ain't dealing with none of this though. It's dealing about lab.
Okay, go ahead.
All right, so I keep forgetting to do the pre-lab and the post-lab questions. So can I just do them over the break?
What you mean you keep forgetting? They right there.
Like I know, but like I don't do them. So it's like I'll do the lab while we in class,